So the next thing we want to talk about is how to solve for a variable in either an equation or in an inequality. So we're going to start by talking about this from the equation standpoint. So I'm going to just replace this inequality symbol with an equal sign and talk about what might be a strategy for getting the x by itself in this equation, which is what it means to solve an equation. Right? Discover what the value of x ought to be. But then once we've talked about it for the equals case, I also want to look at it for the inequality case. So there's greater than or equal to sign here. So we'll get a chance to practice both of those things. So let's start with the equality. If I want to get the x by itself in this equation, what strategies, what steps, what approaches should I be thinking about? I would say the number one rule of the game in working with an equation or working with an inequality is also my earliest memory of algebra was my own father trying to teach me how to do this kind of thing when I was, I don't remember how young I was, but pretty young. He would always tell me, whatever you do to one side, do it to the other side. Do everything to both sides of the equation or the inequality, because otherwise you introduce an imbalance, right? We want the same equation we started with to be equivalent to the equation that we get at the end, so that the solution we find at the end actually has something to do with a question at the beginning. Right? So whatever I do to one side of this equation, I have to do the very same thing to the other side of the equal sign. So for example, if I wanted to, I don't know, if I wanted to make this 4 disappear from the right side, what could I do? I could subtract it. But if I subtract it from the right side, I also need to subtract it from the left side. Right? So if I subtract 4 on the right, it's going to make that 4 disappear. And on the left side, I'm going to have -1 minus 4. By the way, doing arithmetic with negative numbers is going to be, it always takes that extra sort of cognitive step of reminding yourself, how do I subtract -1 minus 4? Well, we're really adding together two negative numbers. And since they're on the same side of 0, we get further away from 0 when we add them together. So -1 minus 4 gives me -5. And then I still have 2/3 x out here in the front. So whatever I do to one side, I have to do to the other side as well. And for linear equations, which are the kind we look at in the first half of our semester, that philosophy is enough to get us all the way to the solution of any equation or of any inequality. Just with a couple of steps that seem like they're kind of wrinkles. One of which is this equation has x appearing on both sides of the equal sign. So if I want to get x by itself, I have to do something about that. How do I get all the x's to be on one side? For example, if I wanted to make this x over here disappear, what can I do? Right, same thing I did with this 4. I can subtract it. So I need to get all my x's to one side, and the way to do that is to subtract one of the x terms, either from the right side or from the left side, and just subtract that term from both sides. When I've done that, my right-hand side, what's x minus x going to become? I've subtracted a quantity from itself. I end up with just plain 0, no quantity left on the right. I still have my -5. And then here I have 2/3 x minus x. Okay, so how do I do that? How do I take two quantities, which are both multiples of x, and subtract them? Let's suppose that I had something simpler, like 6x minus 4x. How would I carry out that subtraction?
Leave the x and subtract the two numbers.
Yeah. So this is similar to what we were doing with fractions a bit ago. We're kind of undoing a multiplication step here, where what I want to focus on is that each of these, 6x and 4x, have an x that's common to both of them. So I'm going to take that x and I'm going to bring it out and write it only once, and write its what we call cofactors, the 6 and the 4, write them separately in their own quantity. So I write the x once, and I subtract the 6 and the 4, and it gives me 2x. This manipulation, by the way, is an artifact of two different things. On the one hand, what we just did is often called combining like terms. These were like terms because they both had the same variable factor, the same variable with the same hidden exponent on it. These are both powers of x to the first, multiples of x to the first. And that means that I can subtract them by subtracting their coefficients, 6 and 4. It's also a reversal of what's called the distributive property of multiplication over addition. What I mean by that is that when I went from the first step here to the second step, what I did was I undid a process where if we were going backwards, we would multiply the x on the outside by the 4 and by the 6 on the inside of the parentheses. The multiplication here, this little secret multiplication, that operation distributing across the subtraction or the addition inside the parentheses. So that would have taken us backwards here, which is why I said we were reversing it. But the distributive property is what makes this tactic of combining like terms actually work. So if I'm going back to our original problem, if I'm subtracting 2/3 x minus x, what I really want to do is write the x only once and write the coefficients inside a set of parentheses. So 2/3, and what's the coefficient on this x that we're subtracting? How many x's are there? If you don't write a coefficient, then there's a secret 1 in front of it. So the total number of x's I should get here is 2/3 minus 1. Well, that again gives me another fraction subtraction that we have to do, which I'll do a little bit more quickly this time. So I write 1 as a fraction first, 1 over 1. Then I need common denominators for 2/3 and for 1 over 1. And common denominators for those are 3, which means I then need to take 1 over 1 and make it into 3 over 3. And then when I subtract 2/3 minus 1/3, I'm going to write my 3 once in the denominator and have 2 minus 3 up in the numerator, and 2 minus 3 is -1. I skipped through a lot of steps there. We're also going to see a totally different way to approach problems like this in just a minute. But if we're doing it this way, this is what we'd end up doing. 2/3 minus 1 gives me -1/3, and that's now the coefficient of my x. And now I'm almost there because I have all my x's on one side, okay, which is something we needed. But we still need to get that x by itself. So to do that, we need to get rid of this -5, and we need to get rid of this -1/3. Which one of these two do you think I should get rid of first? The -5 or the -1/3? What's easier?
-5.
The -5, right. And so the interesting thing about that is that that's a reversal of the order of operations. When I'm solving an equation, I want to worry about subtraction and addition first, before I worry about multiplication and addition, or so multiplication and division. And then all of that before I worry about exponents. And when I work parentheses, when I'm solving an equation, I work from the outside in rather than the inside out. So when we're solving at this point, what we're doing is reversing the order of operations. I want to worry about the subtraction of 5 first, before I worry about the multiplication by -1/3 piece. So what we're really doing is we're undoing the algebra, which knits together the expression on the left. So I'll have -1/3 x equals 5. And now my last step is I'm ready to do the division. Divide by -1/3. And then I will have the x by itself. But it gives me a division problem. 5 divided by -1/3. I'm going to rewrite that using the archaic division symbol that we don't use very often. But I want to use it here to help our process because we haven't talked today about how to divide fractions. So first of all, rewriting 5 as a fraction. Now how do I divide one fraction by another fraction? Yes, flip it and multiply. And when you say it, what am I flipping? Yes, take the second fraction, we call that the divisor, and replace it by its reciprocal. Flip it upside down, right? Take its numerator and make it its new denominator and vice versa. So flip, and, as you said, change the division for multiplication. So those two need to happen simultaneously in order for my new multiplication problem to be equivalent to my old division problem. So 5 over 1 times 3 over -1, multiplied by the reciprocal. And we know how to multiply fractions straight across. 5 times 3 gives me a 15. 1 times -1 gives me -1. And what's 15 divided by -1 better known as? Yeah, we can just call it -15. And so there is then our solution to this equation. So what we had to do to solve this equation was first had to reckon, at some point at least, with the idea that there were variables on both sides. And the way we did that was by subtracting the variable term from one side from both sides, so that all my variables then showed up just on the left in this example. When we carried out that multiplication, we ended up having to combine some like terms. Right? One multiple of x subtracting another multiple of x by subtracting just their coefficients and writing the x only once. So the variable factor here, the x, stayed the same through the process of combining like terms. Once all the variables were on one side, we then just had to reverse the order of operations by worrying about adding and subtracting first, and then worrying about multiplying and dividing to get that variable by itself. So that's an overall sort of overarching strategy for how to get a variable by itself in an equation. But one of the things that we'll see next is that there's a way of handling the fractions in this problem a little differently than we just did. It's a way that I like to use a lot, so I want to make sure to share it with all of you today so you can use it as a tool later on.